Jai Hind. Myself, Nidhi Singh, Assistant Professor in Electrical and Electronics Department, Ajay Kumar Garg Engineering College. Today I am going to discuss topic from Unit 4, that is DC generator. So, the content of this lecture are EMF equation of DC generator, then numerical on EMF equation, then types of DC generator and their voltage equation, and voltage built up in self-excited DC generator, as well as some numericals related to these DC generators and the application of DC generators. So now starting with the EMF equation of DC generator, we know the working principle of DC generator. So DC generator, it operates on Faraday's law of electromagnetic induction, and according to which when the magnetic flux linking a conductor changes, an EMF is induced in the conductor. The value of induced EMF will depend upon some factors like length of conductor, the magnetic field strength, and the speed at which the coil rotates. So now let us see the equation of induced EMF. Here, there are some terms like flux. This is flux per pole in Weber. Then we have Z. This is total number of armature conductors. Then we have N. This is armature rotation in revolution per minute, that is in RPM. Then we have P, that is P stands for number of poles. Then we have capital A, that is number of parallel paths in armature, in which this total number of Z conductors are divided. And then E is the EMF induced in any parallel path, or we can say the total generated EMF of armature. So now according to Faraday's law of electromagnetic induction, we know that average EMF generated per conductor is d phi by dt, that is flux cut by time taken. So flux cut per conductor in one revolution will be, what will be? We know that phi is the flux per pole in Weber, and if there are n p number of poles, so the flux cut per conductor in one revolution will be equal to phi into p. So now next is the number of revolution per minute. So number of revolution, this should be in second. So this will be n by 60. So time taken for one revolution. So now what will be the time taken for one revolution? That will be 60 by n second. So here we can write this d phi is phi p and dt is 60 by n. So this becomes phi p n upon 60. And this is EMF generated by n number of conductors. So what will be the total EMF generated by the armature? So now, therefore, the total EMF generator between the terminal will be given as average EMF generated per conductor into number of conductor in parallel path. So how to find the number of conductor in parallel path? So we know that there are Z number of conductor, and if there are a number of parallel paths, so this Z conductor will get divided into a number of parallel paths. So in one parallel path, you will be having Z by a number of conductors, right? So the total EMF generated will be phi p n 60 into Z by a. So the EMF generated, total EMF generated in armature will be phi p n Z upon 60A. So now if we have a lap type of winding, so in lap type of winding we know that number of parallel path will always be equal to number of poles. And if we are having a wave winding, then this A number of parallel path will always be equal to 2. So now coming to this example, here we have a 4 pole, the number of pole is equal to 4. 4 pole, it is a lap wound DC generator. It has 42 coils. It has 42 coils and with 8 turns. So 42 coils with 8 turns, right? And it is driven at 1120 RPM. If the useful flux per pole is 21 milliweber, calculate the generated EMF and find the speed at which it is to be driven to generate the same EMF as calculated above with wave wound armature. So here you have to calculate the generated EMF. So generated EMF, we know the equation is E is equal to phi p n Z upon 60A. So phi, what is phi given? Phi is given here. This is 21 milliweber. So this is 21 into 10 power minus 3 Weber. So 5 will be 21 milliweber. P is given 4 here. You will put 4 here. And what is N here? N is given 1120. So you will put N is equal to 1120 RPM. Then you need Z. So Z. The Z is not directly given in the question, but you can find this number of conductors. So Z will be equal to, it is given that there are 42 coils and with 42 coils with 8 turns. So 42, you will do 42 into 8. Right? You have 42 coils with 8 turn per coil. Each coil is having 8 turn. So this will be, how many turns will be there? 42 into 8. And we know that 1 turn contains 2 conductor. So it will be multiplied with 2. Right? So you will get the value of Z here. You will put Z here. And you know that this is a lap type winding is here. So A will be also equal to 4 here. Right? Because A will be equal to 4. That is A is equal to number of poles. So if you solve this question, you will get Z is equal to 672. The number of total conductors will be 672. And if you put all these values, you will get 263.42 volt. The next, if it is a wave wound armature, so wave wound armature, so what will be the speed? So in wave wound, we know A is equal to 2. So by putting all the values in this equation, you will get it is coming 560 RPM. Now coming to the types of DC generator. So DC generator, they are classified, they are based on the way in which field windings are excited, how we are exciting the field winding. So we can classify our DC generator. So the different types of DC generators are, the one is separately excited DC generator. Then we have self-excited DC generator, and self-excited DC generator is further classified as shunt generator, series generator and compound generator. And again, this compound generator is classified as long shunt and short shunt. So we will see these classification one by one. So first we will discuss separately excited DC generator. So why this is called separately excited DC generator? It is because the field winding, the supply given to the field winding, we have a separate DC supply. The separate DC supply is connected to the field winding to excite this winding. So this is called separately excited DC generator. So the terms here, this IF, IA, IL, what does this mean? IF means the field current. The current going in this field winding, this is denoted with IF. Then we have IA, that is armature current. IL means load current. RA means armature winding resistance. Armature winding, there is a resistance of winding, so it is denoted as RA. Then VT is terminal voltage. VB is brush drop at the brush contacts. So this is denoted as VB. So if we write the equation for this separately excited DC generator, so we can write E. What is E here? E means the EMF getting generated in this armature. So E will be equal to what? This terminal voltage VT plus drop at this armature, that is IARA, because of armature resistance IARA, and we have brush contact drop, that is VB. So brush contact drop and armature reaction drop if we are considering it. So, and what is this EG? We have already derived the EMF getting induced in the armature. So this E is 5 PNZ upon 60A. This is generated EMF here. Now next, coming to the self-excited DC generator. So what does this self-excited DC generator means? The self-excited generator, this produces the DC output whose field windings are excited by current produced by the generator itself. There is no separate source is used for the field excitation. So in the separately excited, we have seen that we are using a separate source to excite the field winding. But in case of self-excited DC generator, we do not use the separate source, but the excitation is given within the generator only. So in this type of generator, some flux is already present in the poles due to residual magnetism. So when the armature is rotated with the residual flux, what will happen? A small EMF and hence some current is induced in the armature conductor. And now this current will produce more flux, which is then produces more current to flow through the field winding, and it will continue until the field current reaches its rated value. So there is a voltage buildup process in self-excited DC generator. So a small EMF will get generated because of the residual magnetism, and because of that there will be a field current, right? Suppose this is IF1, and now because of this field current more flux will get produced, and because of that more EMF can be induced. And similarly, if this, suppose this is E1, and now because of this EMF now more current is given to the field winding, so this is IF2, and because of this now more EMF will be induced. So likewise this is a cumulative process until or unless it achieves its rated voltage. Now coming to the classification of self-excited DC generator. So there are three types of self-excited DC generator, and based on the way in which the field coils are connected to the armature. So how we are connecting this field winding to the armature, because now this is a self-excited. The field winding is getting the excitation current from the generator itself. So the field winding is connected to the armature, and how it is connected to the armature, the self-excited DC generator is classified as shunt wound generator, then series wound generator, and compound wound generator. So now we will discuss these types of generator one by one. So first is DC shunt generator. So here you can see that this field winding is connected in parallel with the armature. That's why it is called as DC shunt generator. So here this ISH means the shunt field current, IA means the armature current, IL means the load current. Sorry, this is load current. Then RA is armature winding resistance, V is terminal voltage, and VBR is brush contact drop here. So from this diagram only you can relate the relation that IA is equal to IL plus ISH, right? And what will be the value of this ISH? You can see that the voltage across this field winding is VT, right? So you can write here that this ISH is equal to VT upon RSH. What is RSH here? RSH is field winding resistance, right? So IH is equal to VT upon RSH. Now what will be the value of EG? EG will be equal to, EG means the EMF getting induced in the armature. This will be equal to, if you write the loop equation here, you will get EG is equal to VT plus drop in armature IARA plus brush contact drop. So you will get this equation, EG is equal to VT plus IARA plus brush contact drop. Now coming to the DC series generator. So DC series generator, here you can see the field winding is connected in series with the armature, right? So ISC here means the series field current, as it is connected in series, so it is denoted with ISC. Then IA is armature current and IL is load current. RA is armature winding resistance, V is terminal voltage, and VB is brush contact drop. Now from this diagram you can see that this IL is equal to ISC and this is equal to IA. All these currents are equal, right? Now what will be the value of EG? EG will be equal to VT. This is terminal voltage, so we will denote it with sorry, with VT plus we have drop because of this armature resistance, so we have IA, RA. There will be drop because of this field winding, so this will be plus ISC plus RSC plus VB. So this will be the equation for generated EMF, and we know this EG is equal to phi P N Z upon 60A, right? So this will be the equation here. Now coming to the DC compound generator. So DC compound generator has both shunt field winding and series field winding. So one field winding is connected in series with the armature and another field winding is connected in parallel with the armature. So DC compound generator can be classified in two different types based on the way it is connected. So we have long shunt DC compound generator, then we have short shunt DC compound generator. So we'll discuss this one by one. So we have long shunt DC compound generator. So in long shunt DC compound generator, we can see the armature is connected with a series field winding and the shunt field winding is connected across this structure, right? Then this is called long shunt DC compound generator. So in this, shunt field winding is connected in parallel with the combination of series field winding and the armature conductor. So here we can see that this IA and ISC, they both are equal. So IA is equal to ISC here, and we can see here that this IA is equal to ISH plus IL. So we can write IA is equal to IL plus ISH. Then shunt field current. What will the shunt field current? This ISH. What will be this ISH? We can see the voltage across this is V. So we can write V upon RSH, right? So this will be V upon RSH, where we know this RSH is shunt field resistance. Now coming to the what will be this terminal voltage. So this will be EG minus IARA minus IARSC or VBR, or we can write it IA. Why we have IA or ISC, right? Because ISC and IA both are equal. So here, instead of writing ISC, we have written IA here. Now, coming to the short shunt DC compound generator. So in short shunt DC compound generator, the shunt field winding is connected across the armature conductor, and this combination is connected in series with a series field winding. So you can see the shunt field winding is connected across the armature only, right? So here you can see the armature current, right? Here you can see that ISC and IL are equal. So you can write that ISC is equal to IL. And now what about armature current? Armature current, you can see IA is equal to, this is ISH plus IL, right? IA is equal to ISH plus IL. Now, what will be the generator DMF equation? The generator DMF equation, what will be the generator DMF equation? So, this EG will be equal to V plus IA RA plus, you can see that series field winding is also coming. So, you can write ISC plus RSC plus VB, right? So, this will be the generator DMF equation. Now, coming to the voltage drop across shunt field winding, that is ISH RSH. So, shunt field current, what will be the value of shunt field current? This will be equal to EG minus IARA minus VB. So, here this is connected across the armature. So, the voltage across this will be equal to the voltage across the shunt field winding, and that is equal to EG minus IARA minus VB by RSH. Or we can also write it as VT plus ISC RSC. So, from this equation, we can derive that VT plus ISC RSC upon RSS. So, ISH can be calculated in two ways, right? The next, now coming to the example, we have a shunt generator which delivers 450 ampere at 230 volt, and the resistance of the shunt field and armature are 50 ohm and 0.03 ohm respectively. Now here you have to calculate the generated EMF. So first we will draw the generator circuit here. So you can see the generated circuit here. We have to draw the shunt generator. So this is a shunt generator here. So the armature current here, this is the shunt field winding resistance is 50 ohm. This IL is 450 ampere. So here we have to calculate the generator DMF. So what will be the generator DMF here? So we can write EG is equal to V plus IA RA and plus VB. So brush contact drop is not given, so we'll neglect that brush contact drop. So V is given, that is 230 volt. RA is given here. So RA is 0.03 ohm. Here it is given. and you have to find IA first. So you know that here IA is equal to what is ISH plus IL, right? So IL is given 450 ampere, and what will be the ISH? ISH value will be equal to V upon RSH. So V is given 230 and RSH is given 50 ohm. So you can find the value of ISH, IL, and you will find the value of IL, and if you put this value here, you will get the value of generated EMF, right? So if you solve this equation, here you can see that EG is coming 243.6 volt, right? So ISS 230 upon 50, you are getting 4.6. The load current is already given 450. You know IA is equal to IL upon ISH. So IL is given 450 plus 4.6. You have calculated ISH. So you are getting 454.6 ampere. Then you know the equation V plus IARA. So V is 230 given and IARA is given coming 13.6. So you are getting 243.6 volts. So this is the required answer. Now the next example is a 4-pole long shunt lap wound compound generator. It delivers a load current of 50 ampere at 500 volt. The armature resistance is 0.03 ohm. Series field winding resistance is given 0.04 ohm. And the shunt field resistance is 200 ohm. The brush drop may be taken as 1 volt. So now determine the EMF generated. Then calculate also the number of conductors if the speed is 1200 rpm and flux per pole is 0.02 Weber. And here you have to negate armature reaction. So this is the required circuit. This is the long shunt compound, long shunt lap wound compound generator here. So if you will solve, you can find ISH as 500 by 200. So ISH, this is the voltage 500 by 200, you will get 2.5 ampere. Then IA, what will be the value of IA? So IA will be equal to this ISH plus this IL. So ISH you have already calculated, that is 2.5, and IL is given 50 ampere. So after solving this, IA is 52.5 ampere. So series field wind drop you have calculated is 2.1 volt. Then armature drop you have calculated 1.575 volt, and then brush contact drop. So there are two brushes, so it is given 1 volt per brush. So this will be the total brush contact drop will be the 2 volts. So generated EMF will be equal to 500. So what will be the equation for this? You know that EG will be equal to, what will be the equation? V plus IA RA plus ISC RSC plus VP. So this will be the equation. So if you put all the values here, you will get 505.67, right? Now here you have to find the number of conductors. The second part is to find the number of conductors. So to find the number of conductors, you know the generated EMF is, the equation is 5PNZ upon 60A. So if you put all the values here, you will get the number of conductors is coming 1264, right? So this is how you can solve the this example. Now the compound generator, they can be classified as cumulative and differential compound generator. If the two windings, there are two windings, shunt and field, and they are wound on the same pole, we know that. So depending on the direction of winding on the pole, the two fluxes produced by shunt and series field may help or may oppose each other, right? So this fact decide whether the generator is cumulative type or a differential type. So if the two fluxes help each other, like you can see in this first figure, here you can see that the current direction in both the winding in the series and shunt, they are same. So the flux produced by both the winding will be in same direction. So if you hold this winding in the direction of current like this, so you can see the thumb is giving you the direction of the flux, right? So if you hold this, and the finger is indicating the direction of the current, so thumb is indicating the direction of the flux. So you can see that by both the winding, the direction of the flux is downward. So the direction of flux is same. So this type of generator will called as cumulative compound generator. And if the two windings are wound in such direction that the flux produced by them, they oppose each other, then the generator is called differential compound generator. As here you can see that the flux produced by this series, right? If you hold this, you can see the direction of flux is downward. And if you hold this one, the direction, this finger is indicating the direction of the flux, and the direction of the current, and the thumb is indicating the direction of the flux. So here you can see the direction of the flux is upward. So here you can see that flux produced by both the windings are in opposite direction. So this type of compound generator is called differential compound generator. Now coming to the application of various type of DC generator. So we have separately excited DC generator. So as a separate supply is required to excite field winding, the use is restricted to some special applications like electroplating, electro-refining of materials, etc. Then coming to the shunt generator, they are commonly used in battery charging and ordinary lighting purpose. Then we have series generator, commonly used as booster on DC feeder, as a constant current generator for welding generator and arc lamps. Then we have cumulatively compound generator. They are used for domestic lighting purpose and to transmit energy over long distance. Then coming to the differential compound generator, the use of this type of generator is very rare, as it is used for special application like electric arc welding. So it is used very rarely. So these are the application areas of these different types of DC generators. So these are the references which I have referred for this lecture. Jai Hind.